700 million light years from where you're sitting right now, there's a sphere of nothing. Not much.
Nothing.
Picture a region of space so large it should hold 10,000 galaxies, 10,000 islands of light, each one packed with billions of stars, spinning quietly through the dark, the way galaxies do everywhere else in the universe. Now go look at what's actually there.
60. That's it.
60 galaxies rattling around in a space built to hold 10,000. You are looking at a hole in the universe and nobody can agree on how it got there. 330 million light years across. That's the number. 60 galaxies where there should be thousands. And every attempt to explain it runs into the same wall. The math says this thing needed more time to form than the universe has existed. We're going to walk through how this was found, why the timeline doesn't add up, what the loneliest galaxy in the cosmos is doing, sitting dead center in it, and the theories serious scientists float in private but won't put their name on in public. If you want to see where this goes, subscribe now. We begin. Robert Kirshner didn't set out to find a hole in the universe. He was building a map. In 1981, Kirshner led a team at the University of Michigan working on something that sounds simple and is anything but a three-dimensional map of galaxies, real depth, real distance, not just dots scattered across a flat photograph of the sky. To do that, they needed redshift. Here's how redshift works. In plain terms, every galaxy out there is moving away from us as space itself stretches. As a galaxy recedes, the light it sends toward Earth stretches too, sliding toward the red end of the spectrum. It's the same principle as a car engine dropping in pitch as it drives away from you. The faster something moves away, the more that pitch drops. Light does the same thing, just with color instead of sound. Measure how far the light has shifted, and you know how fast the galaxy is receding. Know the speed, and in an expanding universe, you know the distance. So Kirshner's team pointed their instruments at a patch of sky near the constellation Boötes and started logging redshifts, one galaxy at a time, turning flat points of light into a real map with real depth. And then the map did something it wasn't supposed to do. A patch of it came back blank. Not sparse, not thin, blank. Where the team expected galaxies scattered at their usual spacing, they got almost nothing at all. A gap sitting right in the middle of their survey like a page someone forgot to print on. The first move was to assume they'd broken something. They checked the telescope. They checked the calibration. They reran the numbers, looking for the mistake that had to be there, because a gap this size wasn't supposed to exist in anyone's model of the universe. The instruments came back clean. The data held. So they did what any careful team does when a result refuses to behave. They expanded the survey, pushing the boundaries outward, expecting the emptiness to shrink back down to something reasonable once they had more coverage. It didn't shrink, it grew. Every additional slice of sky they added confirmed the same thing. The gap wasn't an artifact of where they'd pointed the telescope. It was real, and it was bigger than the boundaries they'd first drawn around it. Nothing about 1981 cosmology had room for this. Voids were expected in the universe, small ones, modest ones, the normal gaps between galaxy clusters. Nobody had a model that produced something this large, this complete, this stubbornly empty, no matter how far the survey stretched. Kirshner's team had walked into something the textbooks of the time simply didn't account for. When Kirshner's team finally put their findings on paper, they did something you almost never see in astronomy. They put a question mark in the title. Think about that for a second. Scientific papers don't hedge like that. They state findings. They present data and let the numbers make the argument. A question mark in the title is an admission, a way of saying we found this, we checked it 3 times, and we still don't fully believe it ourselves. That's how strange this gap in the sky was to the people who found it. Word got out and other teams didn't wait around. Astronomers elsewhere pointed their own instruments at the same coordinates, running their own surveys, checking their own redshifts, hunting for the mistake that would make this whole thing go away. A calibration error somewhere in the chain. A gap in coverage that made a normal region look artificially empty. Something, anything, that would explain a hole this size without breaking the models everyone had built their careers on. They didn't find it. Survey after survey, using different telescopes, different teams, different methods of measuring distance, all came back with the same impossible answer. The emptiness held. It wasn't a glitch in one instrument or one analysis. It was sitting there in the data no matter who looked or how they looked. That's when the name started circulating. Not in a headline, not in a press release, but the way names actually spread inside a scientific community, quietly, one conversation at a time, one conference hallway at a time. The Great Nothing. There's a reason a name like that moves quietly instead of loudly. Scientists are cautious about theatrical language. Calling something the Great Nothing isn't a neutral description. It's a statement that this thing unsettled the people studying it enough that they reached for language usually reserved for something closer to dread. And once a room full of skeptical astronomers starts using a name like that without prompting, you know the data did something to them that the polite, careful papers didn't fully capture. So the void had a name now, and it had a growing pile of confirmations behind it. What it didn't have was an explanation. And before anyone could even start looking for one, they needed to understand exactly what they were dealing with, because the number everyone kept repeating, 330 million light years, is the kind of figure that sounds almost meaningless until you force yourself to actually sit with what it means. Say it slowly, 330 million light years. Now try to actually picture it, because your brain is going to resist this one hard. Light moves at roughly 670 million miles per hour. That's not a typo. That's just what light does. At that speed, it still takes light about 100,000 years to cross our own galaxy. Tip to tip, one edge of the Milky Way to the other. 100,000 years. And that's just the width of one galaxy among trillions. Now multiply that number by 3,300. That's what you're dealing with when you cross the Boötes Void. Not a bigger version of a normal gap between galaxies. A structure so wide that our entire galaxy, spinning with its hundreds of billions of stars, could be dropped inside it and repeated over and over, billions of times, before you'd fill the space. Not thousands of Milky Ways. Not millions. Billions stacked into a volume that swallows the comparison whole. Here's another way in. The observable universe. Everything we can see, everything light has had time to reach us from since the beginning, spans roughly 93 billion light years. The void alone eats up close to 2% of that entire diameter. 2% sounds small until you remember what it's measuring against, the size of everything. Try it a different way. Imagine lining up galaxies edge to edge like coins on a table, just to cross this void in one straight line. You'd need something like 3,000 of them, side by side, touching, just to span it once. 3,000 galaxies laid end to end, and that only gets you from one side to the other. Now push into volume because diameter alone doesn't do this thing justice. A sphere this size, worked out in cubic light years, produces a number so large it stops functioning as a number and starts functioning as a wall. You can write it down. You can't hold it in your head. Somewhere past a certain point, big and incomprehensible become the same word. And here's the part that should unsettle you more than the size does. Size alone isn't actually the disturbing detail here. A universe this vast is allowed to have big empty patches. Structure formation produces gaps, some of them enormous, and nobody loses sleep over a large void existing somewhere out there in principle. What breaks the picture isn't how wide this thing is. It's what's supposed to be living inside a space that size, and isn't. Run the math the way astronomers run it. Take the average density of galaxies anywhere else in the universe, the normal spacing you'd find in a typical patch of sky, and apply it to a volume the size of the Boötes Void. The answer comes out clean. Something close to 10,000 galaxies should be sitting inside that sphere. Go count what's actually there, and you get 60. 60 galaxies confirmed, sitting inside a space built to hold 10,000. That's not a shortfall. That's a deficit of over 99%. 99.4% of the galaxies this region should contain simply aren't there. Try picturing it at human scale. Take New York City, 5 boroughs, millions of people packed onto sidewalks and subway platforms and stadium seats. Now empty it out until 6 people are left standing in the whole metropolis. 6 people scattered somewhere between Brooklyn and the Bronx, and everyone else just gone. That's the level of emptiness sitting inside the void. Not quiet, not sparse, a city with 6 residents left. And this number didn't drop out of the sky fully formed. Early surveys, working with the equipment available at the time, found 8 galaxies inside the void.
8.
For years, that was the count astronomers had to work with, and it looked less like a supervoid and more like a hard vacuum with a few stragglers caught inside it. Then the telescopes got better. Detectors improved, surveys got deeper, more sensitive, capable of picking up fainter galaxies that earlier instruments had simply missed. Decade after decade, the count climbed. 8 became 20, 20 became 40, 40 eventually settled at 60, and researchers kept expecting that number to keep climbing as instruments kept improving, because that's usually how this works. You build a better telescope, you find more objects. The census keeps growing until it approaches something close to complete. The count stopped at 60, not slowed down, stopped. This is the detail that should sit with you longer than the raw deficit does. 60 isn't a preliminary estimate waiting for the next generation of telescopes to revise upward. Modern surveys working with instruments Kirshner's team could never have imagined have scoured this region and kept coming back with the same number, 60 galaxies. That's not a floor we haven't drilled past yet.
That's the ceiling.
Which means whatever process built this thing wasn't sloppy about it. It didn't accidentally leave behind a scattering of stragglers that better equipment keeps turning up more of. It left exactly the residue it was always going to leave, and the count has held steady long enough that astronomers now treat 60 as a fixed feature of the void rather than a work in progress. A gap this size, this stable, this resistant to every improvement in instrumentation thrown at it, isn't just a description anymore. It's a demand. Something specific had to happen here. Something with a mechanism behind it, because things must have drifted apart somehow. Doesn't survive contact with a number this precise and this permanent. And once you accept that a mechanism is required, you run straight into a problem that no explanation so far has been able to dodge. Gravity, the only force anyone seriously credits with building large-scale structure, doesn't behave anything like what this void needed it to do. Gravity is not a fast worker. Out of the 4 fundamental forces in physics, it's the weakest by a wide margin, and it makes up for that weakness with patience. It doesn't strike, it doesn't push, it doesn't erase. It pulls, slowly, endlessly, one small tug at a time, and it needs enormous stretches of time to turn that tug into anything resembling structure. That's the whole engine behind galaxy formation. Matter clumps because gravity keeps pulling on it, generation after generation, until scattered gas and dust collapses into stars, and stars collapse into galaxies, and galaxies drift into clusters. It's slow. It's the only tool this force has, and it only runs in one direction. Gravity gathers. It does not delete. Scientists did not arrive at that timeline by guessing. They built it, piece by piece, inside a machine. Cosmologists call the process a lambda-cold dark matter simulation, and the setup starts with the oldest photograph anyone has of the universe. The cosmic microwave background radiation left over from about 380,000 years after the Big Bang. That ancient light is not perfectly smooth. It carries faint temperature variations, differences of maybe 1 part in 100,000, and those variations map directly onto tiny differences in density scattered through the infant universe. Feed that density map into a computer as a starting condition, and you have your seed. From there, the method is almost brutally simple. Take billions of particles, each one standing in for a clump of dark matter, or ordinary gas, and scatter them through a simulated volume according to that density map. Then let gravity run. Every particle pulls on every other particle, an unbelievable number of calculations happening at once, and computers handle that load using something called a particle mesh approach, laying a grid across the simulated space and calculating the gravitational pull at each point on that grid rather than tracking every single particle pair directly. Run the clock forward in enormous time steps, recalculate the grid, run it forward again, and repeat that cycle across billions of simulated years. A single run like this can track hundreds of millions, sometimes billions of individual particles spread across a simulated cube, hundreds of millions of light years on a side, updated again and again as the clock advances in steps of tens of millions of years at a time. That's an enormous amount of computation, more than a person could check by hand in 100 lifetimes. which is exactly why these simulations only became possible once computing power caught up to the problem, sometime in the 1990s. What comes out the other end is not a guess. It's a universe grown from the same starting conditions the real one had, evolved under the same gravitational rules, checked against real observations at every stage to make sure the simulated galaxies, filaments, and clusters actually resemble what telescopes see. When cosmologists say gravity alone needs roughly twice the age of the universe to carve out something the size of Boötes, that number isn't intuition. It's the output of a machine that has already proven it can reconstruct the ordinary universe correctly, and still can't reconstruct this. Which is exactly what makes the Boötes Void so hard to sit with once you take it seriously. Those 60 galaxies aren't a footnote, they're the whole case. Their presence proves that matter existed inside that volume at some point in the universe's history, dense enough and organized enough to actually form galaxies. You don't get 60 spinning disks of stars out of nothing. Something had to be there first. Gas clouds thick enough to collapse, matter concentrated enough to ignite. The seeds for structure were present in that region the same way they were present everywhere else in the young universe. So here's the problem. Gravity can't solve on its own. If matter was there once, something happened to almost all of it. Either it got pulled out, dragged away toward denser regions elsewhere, evacuated wholesale from a volume this large, or it never got the chance to clump together at all, stopped somehow before it could organize itself into the 10,000 galaxies the density models expect. Neither of those options sits comfortably inside standard structure formation physics. Notice what both of those options actually require, because the distinction matters more than it first appears. Gravity is a gathering force. Every process it drives, star formation, galaxy formation, cluster formation, works by concentrating matter, pulling scattered material into a smaller, denser space. Removal isn't part of its vocabulary. Gravity has no mechanism built into it for clearing a region out, only for filling one in. Ask gravity to build a galaxy cluster, and it knows exactly what to do. Ask gravity to evacuate a volume this large, this completely, and you're asking it to run backward, against the only direction it has ever been observed to move in. That's worth sitting with using a comparison from somewhere far more mundane than cosmology. Roll a fair die 1,000,000,000,000 times, and somewhere in that trillion rolls you'll get a run of 100 sixes in a row. Nothing about the dice breaks. No rule of probability gets violated. It's a legitimate, technically permitted outcome sitting inside the full range of what randomness can produce. It's also the kind of outcome nobody expects to actually witness, because the odds against it are so long that a single human lifetime, or 100 human lifetimes, wouldn't be enough rolls to expect to see it happen even once. Cosmologists have a term for exactly this kind of result, a rare tail event. Somewhere in the full range of outcomes, a simulation can produce sitting way out at the extreme edge of the probability curve. There's a version of the universe where a void this size and this empty forms within the actual age of the cosmos. It's not mathematically forbidden. Run enough simulated universes, and eventually one of them will spit out something like Boötes on its own. The same way, enough dice rolls will eventually produce that string of 100 sixes. The question that keeps researchers up at night isn't whether it's possible. It's why we happen to be looking directly at the one roll that landed there. Apply that same logic to Boötes, and the discomfort sharpens. This isn't an ordinary gap that showed up somewhere unremarkable in a random simulated universe. It's one of the largest voids anyone has ever measured, sitting exactly where our own telescopes happen to be pointed. Tail events are supposed to be rare enough that you don't expect to find one on your first careful look. Finding one this early, this close, on a survey that only scratched the surface of the observable universe, is the detail that keeps this from feeling like a settled statistical curiosity. Pulling matter out entirely, at this scale, means moving unthinkable amounts of gas and dark matter clear, across hundreds of millions of light years, in a time frame that already strains the age of the universe. Gravity can absolutely relocate matter over cosmic time. What it struggles to do is relocate this much of it, this completely, out of a region this large, on any schedule that fits inside 8 billion years. Every other process, gravity runs points inward. This one would require it to point outward, consistently, across a volume large enough to swallow the Milky Way billions of times over, and nothing in how gravity has ever been observed to behave suggests it works that way. Stopping the matter from clumping in the first place runs into a different wall. If the seeds for structure formation were present here, just like everywhere else in the early universe, something would have needed to actively suppress collapse across the entire volume, uniformly, in every direction, for billions of years running. Gravity doesn't do selective suppression, it just pulls. Explaining why it pulled almost nowhere across a region this size requires something extra, something beyond gravity quietly doing its normal job at a slightly different pace. This is the tension sitting underneath everything else in this investigation. A gap this total, this clean, this resistant to easy explanation can't just be waved away with things drifted apart over time. That phrase works fine for an ordinary gap between filaments. It stops working once you're staring at a hole this large and this empty, because drifting apart is exactly what gravity is supposed to prevent, not cause. So, if the standard picture of matter slowly clumping together can't account for this on its own, the next move is obvious. Build a version of the early universe from scratch, run it forward according to every rule physics actually agrees on, and see whether something this size can ever form naturally given enough time and nothing else. This is where computers enter the case. If gravity working alone can't obviously explain a hole this size, the next step is to actually test it, not with intuition, but with a full simulation of the early universe, built from scratch and run forward according to the same physical laws that govern everything else in the cosmos. Here's how these simulations actually run, step by step, because the process matters as much as the result does. Researchers start by loading in a density map lifted straight from the cosmic microwave background, those faint temperature variations in the ancient light, translated into a three-dimensional starting condition, a snapshot of where matter sat slightly thicker and slightly thinner across the infant universe. That map becomes the seed. From there, the simulation populates a virtual volume with billions of individual particles, each one standing in for a clump of dark matter or ordinary gas, scattered according to exactly those density variations. Then the clock starts. At each step forward, the simulation lays a grid across the entire volume and calculates the gravitational pull acting at every point on that grid, adding up the combined tug from every particle within reach, rather than tracking each individual particle pair one at a time, because tracking every pair directly would take longer than the age of the universe to compute even on the fastest machines available. That grid-based shortcut is what makes a calculation this size possible at all. Once the pull at every point on the grid is known, every particle gets nudged accordingly. Matter shifts slightly toward wherever the pull is strongest, and the simulation advances the clock forward by a fixed step, typically somewhere in the range of tens of millions of years at a time. Then it recalculates the grid from scratch, recalculates the pull, nudges everything again, and repeats. Do that enough times, tens of thousands of steps, billions of simulated years compressed into a run that might take weeks of actual computer time. And what emerges is a universe grown from the same starting conditions. The real one had evolved under the same rules, checked at every stage against what telescopes actually observe to make sure the simulated galaxies, filaments, and clusters resemble anything real. These simulations are good at their job. Run one, and you get a universe that looks a lot like ours. Filaments of galaxies stretched across space, clusters where those filaments intersect, and voids filling the gaps between them. Small voids show up constantly, typically tens of millions of light years across. Medium ones too, stretching into the range of 50 to 100 million light years without much trouble. Every so often, given enough simulated time, you even get something large, a genuine gap pushing past 100 million light years. Rare, but not shocking, sitting at the tail end of what the physics can produce. None of them get anywhere close to Boötes. Push these simulations all the way out to 8 billion years, the actual current age of the universe, and comb through the results looking for anything approaching 330 million light years across, and you come up empty. Not close, but not quite empty. Not give it another few runs empty. The larger structures these models produce top out at a fraction of what's sitting in the sky near the constellation Boötes, missing the real thing by a wide enough margin that researchers had to go back and ask a different question entirely. Not whether the simulations could produce something this large, but how much additional time they'd need before they could. Run the numbers backward, and the estimate that keeps surfacing sits somewhere around 25 to 30 billion years. Not 13, 8, not close to it. Twice that, maybe more, before gravity alone could plausibly hollow out a region this size and leave behind the kind of near total emptiness we're seeing. Sit with that a while, longer than feels comfortable, because the number gets stranger the longer you look at it. Imagine a canyon carved the ordinary way, water and time, and patient erosion cutting through rock, a fraction of an inch at a time. And imagine that canyon needs 2 million years of that steady work to reach the depth and width you're standing in front of. Now imagine the planet underneath it is 1 million years old. Not approximately. Measured, confirmed, checked against multiple independent methods. 1 million years old. No older. And the canyon is still there. Still real. Still exactly as deep and wide as 2 million years of erosion would require. You can put your hand on the rock. You can measure the walls. You can confirm, beyond any reasonable doubt, that this is what a 2 million year canyon looks like. And the clock on the planet says it hasn't existed long enough to have grown one. That's not a discrepancy you shrug off and keep walking. That's the kind of contradiction that makes you check your instruments again. Check the age of the planet again, check the depth of the canyon again, because one of those numbers has to be wrong and none of them are. That's the position cosmologists found themselves in with Boötes. Not off by a rounding error, not a small adjustment away from making the timeline work. The gap between what the universe has actually had time to do and what this structure required sits at a factor of 2 or more, in exactly the wrong direction. The universe isn't old enough for its own structure. The canyon is standing there, fully formed, and the planet hasn't had time to grow it. And here's where the 60 galaxies stop being a side note and start working against the easy explanations. If the void were simply a stretch of space where matter never gathered in the first place, that would still be strange, but it would at least be a single problem, a question about why collapse never got started here. The 60 galaxies rule that version out immediately, spinning disks of stars, actively forming new ones, sitting in a rough line through the void's center. Don't assemble themselves from nothing. Something had to be there once. Gas thick enough to collapse, matter organized enough to ignite fusion and hold a shape for billions of years. The seeds for structure were present in this region exactly the way they were present everywhere else in the young universe. Which means the 60 aren't evidence that softens the timing problem, they're evidence that hardens it. Their existence proves that whatever process emptied this region didn't start with nothing. It started with something, and then had to remove almost all of it on a schedule the simulations already say doesn't fit inside the universe's actual age. It's the difference between a room that was never furnished and a room that was furnished and then emptied out. Every piece gone except for 60 chairs, someone left behind in a line down the middle. The second scenario doesn't just require an explanation for absence. It requires an explanation for a very specific, very thorough removal. And removal on this scale takes more time than gravity has ever had to spend. 60 galaxies scattered through a volume this size could in theory sit anywhere, randomly placed, evenly spread, clustered by chance near one edge. When astronomers actually plotted their positions, the randomness disappeared. The 60 trace a shape, not a sphere filled with scattered points, not a random scatter thinning toward the edges, but something closer to a line, a rough cylinder running straight through the void center. Picture pushing a straw through a beach ball, punching clean through from one side to the other. Now space evenly spaced dots along the length of that straw, 60 of them, stretching the full width of the ball. That's roughly what the galaxy positions look like when you map them in 3 dimensions. A tube of light cutting through an ocean of dark. Getting to that picture took more than glancing at a flat photograph of the sky. A 2-dimensional image can't tell you whether 2 galaxies actually sit near each other in space, or whether one just happens to be sitting 20 million light-years further back, along the same line of sight, stacked in front of the other by pure coincidence of viewing angle. The only way to settle that is with redshift, measuring how far each galaxy's light has stretched, converting that stretch into a real distance, and plotting every one of the 60 in 3 dimensions instead of 2. Once astronomers did that, layering actual depth onto the positions, the picture changed completely. What might have looked like scattered dots on a flat image resolved into a line running straight through real, three-dimensional space. Confirming the line wasn't an illusion took more than a single plot. Researchers ran the equivalent of a fairness test, scattering 60 imaginary galaxies at random throughout a volume shaped like the void over and over thousands of times, checking how often pure chance would produce anything resembling a cylinder on its own. It essentially never did. Random distributions default to clumps and gaps with no particular geometry, not a clean line running pole to pole through the center of a sphere. The tube kept coming back as a statistically significant structure, not a pattern the human eye was inventing out of a handful of dots that happened to look aligned. That shape isn't a curiosity. It's the strongest physical clue anyone has for how this thing actually formed. The leading theory treats that tube as a scar. The idea is that the Boötes Void didn't appear as one single, enormous vacuum all at once. Instead, several smaller underdense regions expanded over billions of years until their edges touched and merged into one continuous void. Where two of those regions met, there would have been a boundary, a thin wall of leftover matter squeezed between them before the merger finished and the wall dissolved into the larger structure. The 60 galaxies in this picture are the fossil of that wall, a filament that got caught in the collision and never fully cleared out. It's a clean story, and it would tie everything together neatly if the details cooperated. They don't. Merger zones, wherever else we see them in the universe, tend to be crowded places. When two underdense regions expand and their edges finally meet, matter gets funneled toward that boundary before the void fully takes shape, the same way debris piles up where two currents collide. You'd expect density there, congestion, a wall thick enough to leave an obvious signature behind. What we're looking at instead is a thread so sparse it's barely distinguishable from the emptiness surrounding it. 60 galaxies is not what a genuine collision zone should look like. It's closer to what's left over after almost everything has already drained away. And there's a second problem sitting inside the shape itself. If this tube really is the aftermath of a recent violent merger between two voids, the galaxies caught inside it should still be showing the effects. They should be getting pulled toward one side or the other, tugged by the residual gravity of whichever void won the collision, still in motion, still settling. They're not doing that. The 60 galaxies sit suspended along that line in something that looks a lot closer to equilibrium, positions that have stabilized rather than positions still being dragged apart by a recent collision. Astronomers checked this directly, measuring the velocity dispersion among the 60, essentially clocking how fast each one is moving relative to its neighbors along the tube. A structure still settling from a violent merger should show a wide spread of speeds, galaxies flung outward at different rates depending on how close each one sat to the point of impact. What shows up instead is a narrow, orderly spread. Speeds bunched close together, consistent with objects that finished whatever motion the merger gave them a long time ago and have simply been drifting since. Whatever happened to put them there, it wasn't recent, and it wasn't violent in any way still visible in how they're moving today. Equilibrium isn't a neutral detail, it's a clock. The same way a flat, undisturbed pond tells you a storm passed through a while ago rather than a minute ago. Water that's just been disturbed still carries ripples, currents, motion that hasn't had time to die down yet. A pond sitting still and level tells you the disturbance is old news, however violent it might have been in the moment it happened. The 60 galaxies read the same way. Structures don't settle into balance overnight, and a tube of galaxies sitting this calmly inside a hole this large implies an age far greater than a quick merger would produce, which drags the investigation straight back to the same wall it hit before, a structure that looks old enough to need time the universe hasn't had to give it. Strip the merger idea down to its simplest version, and it looks almost domestic. Blow soap bubbles into the air and watch two of them drift toward each other. They touch. The thin wall between them collapses, and what's left is one larger bubble where two used to be. Swap soap film for underdense region of the early universe. Stretch the timescale from a fraction of a second to billions of years. And you've got the basic mechanism cosmologists reach for to explain how a supervoid this size could assemble itself out of smaller pieces. The physics behind it isn't controversial on its own. Small pockets of the universe start out slightly less dense than their surroundings. As gravity pulls matter out of those pockets and into the denser regions nearby, the underdense pockets expand. The way a hole in dough gets bigger as the dough around it gets pulled away. Given enough time, two of these expanding pockets can grow large enough that their edges finally meet. At the moment of contact, matter caught in that boundary zone has essentially three options. It can get pulled inward, falling into whichever of the two voids happens to have the stronger gravitational grip. It can escape sideways, swept along into a filament running past the collision point, or it can get stranded, caught in the middle with nowhere obvious to go, drifting in place while the two voids finish merging around it. That third outcome is the one that matters here, because it's the only one that leaves anything behind. A thread of stranded matter, sitting exactly where two voids used to meet, is precisely the kind of leftover structure that could explain a thin line of galaxies running through the center of a much larger emptiness. Run this through a computer simulation, and the shape holds up reasonably well. Models built to test void mergers do produce something that looks, in a general sense, like what we're describing: a large combined void with a sparse filament threaded through its middle, marking the old boundary. As a rough sketch of the geometry, the soap bubble picture earns its place. The trouble starts when you ask what it takes to get two voids that size in the first place. For a merger to produce something on the scale of the Boötes Void, the component voids feeding into it can't be ordinary. They need to already be unusually large before they even touch, well beyond the typical range simulations tend to produce on their own. You're not explaining one improbable structure with two normal ones. You're explaining one improbable structure by requiring several other improbable structures to exist beforehand, in the right places, at the right sizes, ready to collide. There's a comparison that captures how uncomfortable this gets. A tornado can, in principle, assemble a car. Every part obeys the laws of physics. Nothing about it violates a single rule. It's just wildly improbable that wind alone would ever sort scattered parts into a working engine, a chassis, four wheels in the right positions. The soap bubble model works the same way. Technically permitted, not remotely the kind of thing you'd expect to happen without something else nudging the odds. And that's exactly where dark energy starts pushing its way into the case file. In 1917, Einstein added a term to his equations that he called the cosmological constant. He wasn't trying to predict anything new. He was trying to keep the universe still, because a static universe was what everyone at the time expected space to be. When observations later showed the universe wasn't static at all, that it was expanding, Einstein pulled the term back out and reportedly called it the biggest blunder of his career. Decades passed. Then astronomers studying distant supernovae found something Einstein's original instinct hadn't anticipated. The expansion wasn't just happening, it was speeding up. Something was pushing space apart and pushing harder over time. The old cosmological constant got dusted off, given a new name, and dark energy walked onto the stage as one of the least understood, most consequential quantities in physics. Here's the distinction that matters for this investigation. Dark energy doesn't shove galaxies through space the way one object pushes another. It stretches space itself, expanding the fabric that galaxies are sitting on. 2 points with nothing between them but empty space will drift apart simply because more space is being generated in the gap, whether or not anything is physically moving through it. That distinction is why dark energy stays invisible almost everywhere you'd normally look for it. Inside a galaxy, gravity is doing so much of the work, holding stars in orbit, binding structure together, that dark energy's contribution gets buried under forces that are billions of times stronger at that scale. You won't find its fingerprints in a solar system. You barely find them in a galaxy cluster. It only becomes the dominant player once you're looking across hundreds of millions of light years, where gravity has thinned out enough to stop drowning it out. Which makes a structure like Boötes close to the ideal place to go looking for it. Inside a void this empty, there's almost no matter left to generate any competing gravitational pull. Dark energy isn't fighting anything for control of the outcome. It's simply expanding a region that has nothing left inside it strong enough to resist. Researchers have measured the void's expansion rate directly, tracking how quickly its boundaries are still growing today. What they find matches what you'd expect if dark energy is spread uniformly through the universe, the same strength everywhere rather than somehow concentrated or intensified inside this particular region. The void isn't expanding because something unusual is happening locally. It's expanding because dark energy is doing exactly what it does everywhere else. And here, with nothing left to oppose it, that effect gets to run unopposed. That's a real answer, and it's not a small one. It explains why the void keeps growing right now, why its edges are still pushing outward this very moment, billions of years after the fact. It does not explain how the void got large enough in the first place to reach that stage. Uniform dark energy accounts for ongoing growth. It says nothing about how a structure this size and this empty formed early enough to already be sitting there, waiting to expand, long before dark energy became the dominant force in the universe at all. So, how empty is empty exactly? Not as a feeling.
As a number.
Spread 60 galaxies across a sphere, 330 million light-years wide, and the spacing works out to roughly one galaxy every 5 million light-years of open space. That's the void, reduced to a single figure. One island, then 5 million light-years of absolutely nothing, then another island. To feel how strange that is, you have to build a ladder and climb it. Earth's atmosphere at sea level is packed with something like 10 quintillion molecules in a single cubic centimeter. So dense, you never think about the air being there at all. Step into the best vacuum chamber humans have ever built in a laboratory, and you've dropped that number by a factor of 1 trillion or more, down to a few thousand molecules bouncing around in that same space. Already that sounds close to nothing. It isn't. Go out to interplanetary space, the gap between Earth and the outer planets, and the count drops again, down to just a handful of particles per cubic centimeter, mostly stray protons and electrons streaming off the sun. Push further into interstellar space, the room between stars inside our own galaxy, and you're down to roughly 1 atom per cubic centimeter, sometimes less. That's the number astronomers usually reach for when they want to describe true emptiness. The void sits below all of it, not by a small margin. The intergalactic gas that normally drifts through the space between galaxies, thin as it already is out there, thins out even further inside Boötes. Whatever baseline of particles you'd expect to find scattered, through a typical stretch of cosmic emptiness, this region comes in under it. Which means a photon crossing the void isn't just unlikely to hit something. It's crossing 330 million light-years with functionally nothing in its path capable of stopping it. No scattering off gas. No absorption by dust. No detour caused by a stray atom nudging it off course. It goes in one edge and comes out the other, essentially unchanged, because there was never enough matter in between to touch it. Neutrinos make the case even stranger. These particles barely interact with anything under normal circumstances, and inside a region this stripped of matter, that already rare interaction becomes close to non-existent. A pattern of neutrinos entering one side of the void could in principle cross the entire span and emerge on the other end in close to its original form, untouched by the kind of scattering that would scramble it anywhere denser. That property turns the void into something more than an empty room. It starts to look like an accidental time capsule, a stretch of space capable of carrying information across hundreds of millions of light years without the usual static and interference scrambling the signal along the way. And once you realize the void can preserve things that cleanly, the next question isn't just what's missing from it. It's what you could actually learn by using that emptiness on purpose. Dark matter never shows up on camera. It doesn't emit light, doesn't block light, doesn't do anything a telescope can capture directly. Everything we know about it comes from watching how it pulls on the things around it. And that kind of measurement gets messy fast in crowded regions of space where galaxies' gas and dark matter are all tangled together, each one tugging on the others, each signal blurring into the next. The void strips that mess away, with almost nothing else present to muddy the picture. Whatever gravitational signal does show up inside Boötes has far fewer places to hide. Researchers turned to gravitational lensing to take advantage of that, measuring how the light from galaxies behind the void gets bent on its way to us. Mass bends light, whether that mass is visible or not, and the amount of bending tells you how much total mass is sitting in the way, dark matter included. What they found: the void carries something like 10% of the matter density you'd expect in a typical patch of the universe. Not zero. Not close to zero. Just a small fraction of normal, spread thin across an enormous volume. The more interesting number sits inside that 10%. Break it down into dark matter and ordinary matter separately, and the ratio between them matches the cosmic average almost exactly. Whatever process hollowed out this region didn't play favorites. It didn't strip out galaxies while leaving dark matter behind, and it didn't do the reverse either. Both went missing together, in the same proportion you'd find anywhere else in the universe. That single detail rules out an entire category of explanation. Any theory built on something selectively removing normal matter, some mechanism that specifically clears out gas and stars while sparing the dark matter scaffolding around them, doesn't survive contact with this ratio. Whatever emptied this place out, treated both kinds of matter as the same problem to solve. The void's thinness also makes it useful for a different kind of test entirely, checking whether Einstein's equations still hold up out here, or whether gravity starts behaving differently once you're working across hundreds of millions of light years with almost nothing around to interfere. Modified gravity theories exist precisely because some researchers suspect general relativity might need adjustment at the largest scales, and a region this stripped down offers about as clean a testing ground as you could ask for. Track how the 60 galaxies move, compare that motion against what standard gravity predicts, and any deviation should stand out clearly, with nothing else around to explain it away. It doesn't stand out. The motion of galaxies inside the void lines up with what Einstein's equations say it should be. No unexplained drift, no unaccounted for pull, nothing hinting that gravity is quietly doing something different out here than it does everywhere else. Whatever built the Boötes Void, it isn't a broken version of gravity. The same rules that hold everywhere else in the cosmos are holding here too, which leaves the void doing exactly what a clean laboratory is supposed to do, ruling things out one at a time, narrowing the list of suspects, without yet handing over the culprit. And there's one more kind of physics this emptiness is uniquely built to test, one that has nothing to do with matter at all, and everything to do with a particle that barely interacts with anything in the first place. Every second, something like 100 trillion neutrinos pass straight through your body. You don't feel it.
You never will.
These particles interact with matter so rarely that a solid wall of lead a light year thick still wouldn't be enough to guarantee stopping one. They pour out of the sun, out of supernovae, out of the leftover afterglow of the Big Bang itself, streaming through planets and people and stars like none of it is actually there. That makes them almost impossible to study directly. On Earth, physicists have to bury massive detectors deep underground, surrounded by tons of shielding, just to catch the occasional rare interaction that gives away a neutrino's presence at all. And even with all that effort, one of the biggest unanswered questions in particle physics remains stubbornly out of reach. How much do neutrinos actually weigh? Not their type, not their behavior in bulk, but their absolute mass. The number that would settle one of the last open questions in the standard model of physics. The Boötes Void offers something no laboratory on Earth ever could. A clean, straight, 330 million light-year baseline, with almost nothing in the way to interfere with a signal traveling through it. Measuring neutrino mass usually depends on watching these particles change identity over long distances, a process called oscillation, and the accuracy of that measurement depends heavily on how long a baseline you can work with. Longer distances mean more oscillation cycles to observe, and more oscillation cycles mean a sharper, more precise answer. Earth-based detectors are stuck working with baselines measured in hundreds or thousands of miles. The void offers a baseline that dwarfs anything achievable on Earth, a stretch of space so undisturbed that a neutrino signal crossing it would arrive on the other side with almost none of the usual static scrambling the result. Supernova neutrino bursts make the case even sharper. When a massive star collapses, it releases a flood of neutrinos seconds before any visible light escapes, carrying information about the collapse itself straight out into space. If a burst like that happened to cross the void, it would emerge on the far side essentially undistorted, a clean signal instead of the scattered, degraded version astronomers usually have to work with when detecting these events from crowded regions of the galaxy. Here's the part that sits uneasily once you actually think it through. If a signal like that can cross the void with almost nothing to disturb it, there's no reason to assume this hasn't already happened. Ancient neutrino bursts, released by stars that died hundreds of millions of years ago, could be threading their way through that emptiness right now. carrying information nobody has built the instruments to catch yet. Not hypothetical signals waiting to be sent, signals that may already be in transit, uninterpreted, passing through a hole in space nobody was watching closely enough to notice. And this same emptiness that makes the void useful for tracking particles too small to see is exactly what makes it useful for tracking something else entirely, its own edges and how fast they're still moving outward today. Here's something researchers didn't expect when they started tracking the void's edges closely. The galaxies sitting right at the boundary are moving outward faster than plain cosmic expansion should account for. Ordinary expansion carries everything apart at a predictable rate, the same background stretching that separates galaxies everywhere in the universe. Galaxies at the rim of Boötes aren't just riding that background stretch. They're moving away from the void's center with extra speed on top of it, an added push that shows up clearly once you isolate it from the general expansion everyone already expects. Think of it like a bubble with pressure still building on the inside, pushing outward against its own boundary, rather than just drifting along with everything around it. That's roughly the behavior astronomers are seeing. The void isn't a static hole that happens to be expanding along with the rest of the universe. It's acting like something still actively growing from within, still shoving its own edges outward under its own momentum. That extra motion turns out to be useful for more than just describing what's happening today. Run the expansion rate backward, the same way you'd rewind a video to see where something started, and you can estimate roughly when the void first began forming. The math lands somewhere between 10 and 12 billion years ago. Sit with that number for a second. The universe itself is 13.8 billion years old. A formation estimate of 10 to 12 billion years doesn't leave much runway. It places the void's origin uncomfortably close to the universe's own early history, back when galaxies themselves were still assembling for the first time. Whatever hollowed this place out started doing it almost as soon as there was a universe available to hollow out. There's a comparison worth drawing here, and it comes from the neighborhood surrounding the void rather than the void itself. Superclusters sitting nearby carry enough mass to exert real gravitational pull on their surroundings, the kind of pull that should, in principle, be dragging on the void's expanding edges and slowing them down. Gravity from that much matter doesn't just sit there quietly, it reaches outward and tugs. It isn't working. The void's boundaries show no sign of that expected drag, no measurable slowdown from the gravity of everything sitting just outside them. Whatever force is driving this expansion is outrunning the pull of some of the most massive structures in the nearby universe, continuing to push outward as if that surrounding mass barely registers at all. An expansion rate measured this cleanly, this precisely, stops being just a description of one strange void. It becomes a tool, something that can be pointed at a much larger argument currently splitting cosmology down the middle. Because the rate at which the universe is expanding, measured different ways by different teams using different methods, keeps producing answers that don't agree with each other. And a supervoid this size, expanding this precisely, this measurably, turns out to be exactly the kind of object capable of testing which side of that disagreement is actually right. There's a number cosmologists have been fighting over for more than a decade, and it should be the simplest number in the entire field. How fast is the universe expanding right now? Two completely independent methods try to answer that question, and they give two different answers. Not close enough to round different, actually different outside the margin of error, in a way that's had physicists checking each other's math since the disagreement first showed up. One method reads the expansion rate off the cosmic microwave background, the leftover light from the early universe, run through the standard model of cosmology to predict what expansion should look like today. The other method skips the early universe entirely and just measures nearby objects directly, distant supernovae and pulsating stars with known brightness, using them as mile markers to clock how fast everything is actually receding right now. Those two methods should agree. They don't. The gap between them sits at roughly 9%, and every attempt to explain it away as a measurement mistake has failed to make it disappear. This is the Hubble tension, and it's currently one of the deepest open wounds in cosmology. One proposal for closing that gap points somewhere nobody expected to look, not at the equipment, not at the math, but at our own address in the universe. The idea is that we happen to be living inside, or at least very near, a large underdense region cosmologists call the KBC void. If that's true, the local measurement wouldn't be catching the universe's true expansion rate at all. It would be catching a distorted version of it, skewed by exactly the kind of neighborhood we happen to occupy. Here's the mechanism behind that distortion. Sit near the edge of an underdense region, and the gravity pulling on you isn't balanced the way it would be in an average patch of space. There's less mass nearby pulling inward, and more mass further out in the denser regions beyond the void's boundary pulling outward. That imbalance gives everything near the edge an extra shove, a peculiar velocity layered on top of the universe's ordinary expansion. Astronomers call this outward peculiar velocity, and it's not exotic physics. It's just gravity doing what gravity does, responding to whatever mass happens to be nearby and whatever's missing. Layer that extra push on top of standard cosmic expansion, and the local measurement comes out running hot. Objects near us look like they're receding faster than the true cosmic average, not because the universe itself is expanding unevenly, but because our own position is quietly adding velocity that has nothing to do with universal expansion at all. The measurement isn't wrong. It's just measuring something slightly different than what it thinks it's measuring. If that explanation holds, it means our own neighborhood is already distorting one of the most fundamental numbers in physics, simply by virtue of where we happen to be sitting. Which raises an uncomfortable follow-up question. If a modest local underdensity can bend a measurement this significant, what happens when you look at a structure that takes that same effect and pushes it to its absolute extreme? Boötes isn't a small underdense neighborhood biasing one calculation. It's the full-scale version of the same problem, playing out at a size that makes the KBC void look almost restrained by comparison. The KBC void isn't a small dent in the local neighborhood. It spans roughly 2 billion light-years across, and inside that volume matter runs about 20% below the cosmic average. That's not a subtle deficit. It's a genuine, measurable hole in the universe's density, and we're not looking at it from a safe distance. We're inside it. The Milky Way itself carries a peculiar velocity of about 600,000 miles per hour, motion layered on top of the universe's ordinary expansion. Part of that speed comes from exactly the mechanism described a moment ago, gravity pulling us outward, away from the underdensity we're sitting in, toward the denser structures beyond its edge. We're not just measuring a void from the outside, we're being pushed by one right now at 600,000 miles an hour. Here's where the discomfort sets in. Standard cosmology runs on an assumption called the cosmological principle, the idea that no location in the universe should be special. Zoom out far enough, and every region should look statistically the same as every other region. No privileged neighborhoods, no unusual pockets, just an even distribution of matter, once you average over a large enough volume. Finding yourself inside a 2 billion light-year underdensity doesn't fit that principle comfortably. A void this size, sitting exactly where our own galaxy happens to be, should be rare under standard models, the kind of structure you'd expect to encounter maybe once in 1,000 random samplings of the universe, if that. And yet here we are, not adjacent to it, not near its outer edge, but living inside it, using it as the baseline for every measurement we make about the rest of the cosmos. That's not a comfortable position for a science built on the assumption that its observers occupy an unremarkable vantage point. Researchers generally prefer boring answers. A universe where every neighborhood looks roughly like every other neighborhood is a universe where your measurements can be trusted at face value, extrapolated outward without much worry that your particular corner of space is secretly warping the results. A universe where you happen to be sitting inside a statistically rare underdensity is a universe where you have to ask constantly whether what you're measuring reflects the cosmos as a whole or just the strange pocket you happen to be occupying. There's no way to fully resolve that tension yet. The cosmological principle predicts we shouldn't be here. The data says we are. Both of those things are true at the same time, and cosmology hasn't found a way to make them stop contradicting each other. Which is exactly why Boötes matters to this argument. The KBC void shows what a modest version of this problem looks like, when it's biasing measurements we depend on every day. It's an underdensity we can study up close, precisely because we're living inside it. Boötes takes that same basic anomaly, the same violation of an assumption cosmology treats as close to sacred, and pushes it to a scale that makes our own neighborhood look almost conservative by comparison. If a 2 billion light-year void sitting under our own galaxy already strains the numbers, a 330 million light-year void this deep, this symmetric, this empty, forces the same question back into the room with nowhere left to hide. Shapes carry information. Long before anyone measures density or age, the basic outline of a structure tells you something about the forces that built it, and that's exactly why the actual geometry of Boötes keeps bothering the people who study it. Gravity is not a tidy sculptor. Matter clumps unevenly, pulled by whatever happens to sit nearby, dragged harder in some directions than others depending on the accident of what formed where. Run that process on any underdense region, and the natural result should be lumpy, elongated in one direction, pinched in another, stretched wherever a nearby filament happened to pull harder than its neighbors. Irregular isn't a flaw in void formation, it's the expected outcome. Boots doesn't look like that, measured across its width in every direction. The void comes back close to spherical, the same rough diameter, no matter which axis you check it against. That's not the geometry gravity usually leaves behind. A structure built by uneven pulling over billions of years should show the scars of that unevenness somewhere in its outline. This one barely shows any. The surroundings only sharpen the strangeness. 5 separate superclusters ring the void, sitting at distances from its center that land in roughly the same range rather than scattered at random. Picture the points of a geometric solid, evenly spaced around a central hollow, rather than the lopsided arrangement you'd expect from clusters that formed independently, each pulled into position by its own local history. 5 massive structures, roughly equidistant, wrapped around one void, like they were placed rather than accumulated. If the merger picture from earlier holds, this symmetry becomes even harder to explain. Smaller voids combining into a larger one should leave seams, the visible aftermath of boundaries where 2 regions met and dissolved into each other unevenly. Real mergers are messy. They leave traces, thickened patches, slight asymmetries where one void's edge pushed further than the others before the whole thing settled. None of that shows up here. The boundary is smooth in every direction. Without the lopsided residue, a genuine collision between unequal partners should leave scattered across its rim. One other candidate falls away almost immediately, once you check it against the record. An early universe explosion, some violent release of energy pushing matter outward from a single point, would leave a heat signature behind, a detectable pattern baked into the cosmic microwave background where that burst first went off. Astronomers have looked. There's no matching signature anywhere near this location. No scorch mark in the ancient light, consistent with an outward blast of that scale. Whatever hollowed out Boötes, it wasn't an explosion, and the absence of that signature closes off one of the simpler explanations before it can even get started. What's left is a void that looks less like the product of ordinary gravitational unevenness and more like something built to a specification nobody has identified. That kind of precision doesn't sit comfortably with standard cosmology, and it's exactly the sort of detail that pushes some researchers away from asking how the void formed and toward a stranger question entirely. What, if anything, is sitting at its center? Every void that forms through drainage should leave something behind at its exact middle. If matter is flowing outward from a central point toward the walls of a growing bubble, that flow doesn't need to be perfectly clean. Some residue should linger, a thin scrap of gas too slow to escape, a dwarf galaxy that never fully formed, some leftover trace marking the spot the emptying process started from. That's how drainage works everywhere else in physics. The last bit out the door is rarely nothing at all. Point every instrument available at the exact center of Boötes, and you get nothing. Not faint traces, not an ambiguous smudge that might be something. Radio surveys, infrared scans, X-ray observations, all aimed at the same coordinates, and all of them come back with the same answer. No object, no energy source, no anomaly of any kind sitting where the geometry says the center should be. That absence has pushed some researchers towards stranger candidates than ordinary leftover debris. The primordial black hole idea gets floated fairly often. The notion that some enormous black hole formed in the earliest moments after the Big Bang, rather than from a collapsing star, could sit at the void's core and account for the emptiness around it. The problem is that black holes of that scale don't stay invisible. They should be detectable through their gravitational pull on anything nearby. through lensing effects on background light, through some measurable signature betraying their presence. None of that shows up here. Whatever fills that central point, it isn't hiding a black hole large enough to explain a void this size. The naked singularity idea goes further still and asks for more in exchange. A naked singularity would be a point of infinite density sitting out in the open, without an event horizon wrapped around it, to keep its effects contained the way a black hole does. The trouble is that physics has a rule against this happening under normal conditions, an assumption called cosmic censorship, which holds that singularities should always come cloaked, hidden behind a horizon, rather than left exposed to the rest of the universe. Building a naked singularity into this explanation means setting that assumption aside entirely, and doing so without a shred of independent evidence that cosmic censorship ever fails anywhere else. That's a heavy price to pay for filling in one gap, which leaves the least satisfying answer as also the most honest one. The center of the void appears to contain exactly what it looks like it contains. Nothing measurable, nothing detectable, no residual object marking where matter used to be. And that plain absence is stranger than any of the exotic alternatives, precisely because it refuses to explain itself. A hole this size, this deliberate looking in its symmetry, ought to have left something behind at its heart. It didn't. With the center offering no answers, the investigation has nowhere left to go but outward, back toward the only concrete evidence anyone has ever pulled out of this place. The 60 galaxies are still out there, still refusing to behave the way isolation should make them behave. Isolation is supposed to leave marks. That's the working assumption behind decades of galaxy formation theory, and it's a reasonable one. A galaxy that spends billions of years without a single close neighbor, without mergers, without gravitational interactions of any kind to stir things up, should look different from one that grew up in a crowded neighborhood. Astronomers built models around exactly that prediction. Cut a galaxy off from outside contact for long enough, and it should show the damage. Stunted growth, strange chemical ratios, structure that never quite finished forming, because nothing ever came along to push it the rest of the way there. The 60 galaxies inside Boötes don't cooperate with that prediction. Pull their spectra and measure the elements inside them, and the numbers come back ordinary. Carbon, oxygen, iron, all present in roughly the proportions you'd expect from a galaxy that went through a completely typical stellar history, generation after generation of stars living, dying, and seeding the surrounding gas with heavier elements along the way. Nothing about their chemical fingerprint marks them as isolated. They read like galaxies pulled from anywhere else in the universe. Star formation tells the same story. These galaxies aren't running on fumes, coasting toward a slow shutdown the way isolated systems are supposed to. Several of them are still actively forming stars at rates that hold up against galaxies sitting in far denser regions, pulling gas from somewhere and converting it into new stars on a schedule that shouldn't be sustainable without outside help topping off the supply. Structure is where the mismatch gets hardest to explain away. Spiral arms aren't permanent fixtures. Left alone, without periodic gravitational nudges from a passing neighbor to refresh the pattern, a galaxy's spiral structure should gradually wind itself tighter, blur, and eventually smooth out into something closer to a formless disk. That process takes time, but it's not optional. It's basic galactic dynamics, the same way a spinning top eventually loses its clean rotation without something tapping it back into line. The void galaxies keep their spiral arms crisp, well-defined, distinct, the kind of clean structure you'd expect from a galaxy that's had regular interactions keeping its pattern sharp, not one that's spent the entire age of the structure surrounding it with nothing nearby to interact with at all. That's the tension sitting underneath all of this. Isolation is supposed to show up somewhere in the data, in the chemistry, in the star formation, in the shape of the thing itself. It mostly doesn't. These 60 galaxies have spent an enormous stretch of cosmic time cut off from the kind of contact that theory says should have marked them by now, and they look by almost every measure available, like galaxies that never got the memo about where they were living. One of them in particular has become the object everyone points to first when this puzzle comes up. Not because it's stranger than the rest, but because it's the clearest possible example of just how far this contradiction goes. Its catalog number reads like a barcode, MCG plus 01-02-015. No poetry in the name, Nothing to suggest why astronomers keep coming back to this one specific galaxy out of the 60 scattered through the void. But sitting deep inside Boötes, cut off from any neighbor for something close to 100 million light-years in every direction, this galaxy has earned a title none of its catalog numbers hint at. Some call it the loneliest galaxy known. For years, it wasn't even classified correctly. Early observations read it as a featureless elliptical, a smooth blob of old stars with nothing interesting going on structurally, the kind of galaxy you'd expect from a system that finished evolving long ago and simply stopped changing. That classification held until Hubble imaging looked closer and found something the earlier surveys had missed entirely: spiral arms. A central bar cutting across the core in the kind of structured pattern that shouldn't exist in a galaxy assumed to be a dead, shapeless remnant. The elliptical label was wrong. This was a barred spiral, fully formed, sitting alone in the dark. Its gas tells its own story. Astronomers studying its composition describe it as close to untouched, chemically similar to what you'd expect if nothing from outside had reached in and altered it since somewhere near the early universe. No neighboring galaxy has fed it fresh material. No merger has stirred its reserves or introduced anything foreign into the mix. Whatever gas this galaxy has, it's largely been sitting there, undisturbed, for an enormous stretch of cosmic time. And yet it's still forming stars, actively, at rates that shouldn't be sustainable under the assumptions built into most galaxy evolution models. Star formation eats through a galaxy's gas supply. Left alone long enough, without some outside mechanism replenishing what's been consumed, that supply should run thin and star formation should taper off toward quiet. MCG plus 01-02-015 hasn't gotten the memo. It keeps producing new stars on a schedule that implies either an internal gas reserve far larger than expected, or some process nobody's fully identified quietly keeping the fuel line open. The bar and spiral pattern raise the same question from a different angle. As established earlier, spiral structure needs periodic refreshing, some external gravitational nudge to keep the pattern from winding down into a featureless disk. This galaxy has had no such nudge available to it, not for tens of millions of years, not from anything close enough to matter. And its structure holds anyway, bar and arms both, sharp enough that nothing about its appearance would tell you it spent its entire existence with nothing nearby. That combination is exactly what makes this particular galaxy the one researchers keep returning to. Every other void galaxy shares some version of this puzzle, but MCG plus 01, 02, 015 offers the cleanest version of it, a single system isolated enough, studied closely enough to function as close to a controlled experiment as galaxy evolution gets. No environmental noise, no nearby interactions to complicate the picture. Just one galaxy, entirely on its own, doing things current models say it shouldn't be able to do without help it clearly never received. Which raises a question worth sitting with for a moment longer than the data alone requires. Somewhere inside that galaxy, if a planet happens to orbit the right kind of star, whatever inhabitants might be looking upward would inherit a version of the universe built on an entirely different set of assumptions than the one we grew up under. Stand on that world for a moment. Whatever planet might be circling that star inside that galaxy, at the center of all that isolation.
Look up.
Your own galaxy stretches overhead the way it does here, a river of light bending across the dark. That part hasn't changed. But keep looking past the edge of that band of stars, out into the space beyond it, and there's nothing waiting for you. No Andromeda. No faint smudge of a neighboring galaxy hanging low near the horizon. The kind of thing early astronomers on Earth spent centuries staring at without quite understanding what they were looking at. Just your own galaxy. And then true black, unbroken, for as far as any instrument could reach. Now put Galileo on that world instead of this one. Hand him the same telescope, aimed at the same patch of sky, and let him look at whatever passes for planets in that system. On Earth, that telescope found Jupiter's moons, 4 points of light swinging around a world that wasn't supposed to have anything orbiting it, and that single observation cracked open an entire way of thinking about the cosmos. It forced the question of what else might be moving out there, unseen, waiting to be found. On a world inside Boötes, point that same telescope in every available direction, and it comes back with nothing to reframe. No moons revealing an unexpected order. No hidden motion contradicting an old model. just confirmation that things are exactly as they appeared to the naked eye. The telescope becomes a tool with nothing new to say. Push the timeline forward. On Earth, it took until 1924 for anyone to prove that other galaxies existed at all, when Edwin Hubble resolved individual stars inside Andromeda and settled a debate that had dragged on for years. That discovery depended entirely on Andromeda being close enough, bright enough, to resolve with the instruments available at the time. Strip that nearby galaxy out of the sky, and the discovery doesn't happen on schedule. Push the nearest visible neighbor out to tens of millions of light years instead of a few million, and you've pushed the tools required to detect it out by decades. Maybe the confirmation doesn't land until the 1960s. Maybe later. An entire foundational discovery in cosmology, delayed by nothing more than an accident of address. That delay would have shaped more than astronomy. Cosmology on Earth grew out of connection, the recognition that our galaxy was one among countless others, scattered across a universe built on the same repeating pattern everywhere you looked. A civilization growing up inside Boötes wouldn't have that framework available to lean on. Their cosmology would have to be built around isolation, instead a science constructed on the assumption that structure ends at the edge of their own galaxy because for most of their history, nothing would have given them reason to think otherwise. Same physics, same laws, a completely different starting point for understanding what any of it means. None of this is really about them, though. It's a thought experiment aimed at a mirror, because the only reason this scenario is worth building out in this much detail is what it reveals about the vantage point we already occupy, the one we've never had to question. Sitting in a stretch of universe crowded enough that a discovery like Hubble's arrived exactly when it was supposed to. Our own address did the opposite of what Boötes would have done. It handed us the universe early, worth asking what else that same accident of address might be quietly deciding for us, right now, without anyone noticing. Copernicus started something he probably didn't fully appreciate at the time. Move the Earth out of the center of the solar system, and you're not just correcting an orbital diagram. You're opening the door to a much bigger demotion, one that hasn't really stopped since. The Sun turned out to be an unremarkable star among billions. The galaxy turned out to be one among countless others, scattered across a universe with no center at all. Each step moved humanity further from any position that might be considered special. That's the trajectory the cosmological principle sits on top of, the working assumption that our patch of the universe is exactly as unremarkable as every other patch, once you zoom out far enough to average things fairly. The KBC void complicates that story in a way that's easy to miss if you're not looking closely. For all the ways science has pushed humanity away from the center of anything, our own neighborhood has quietly turned out to be statistically unusual, sitting inside an underdensity that shouldn't be common enough for us to be occupying it by simple chance. Not special in the sense of significant, special in the narrower, more uncomfortable sense of being an outlier, a location that stands apart from the average distribution the cosmological principle assumes we should be sitting in. Run the numbers on how often a void of that size should show up under standard models, positioned exactly where an observer happens to be located, and the answer comes back rare. 1 in 1,000 may be rarer, depending on which model you're running and how generously you define the boundaries. That's not a void tucked away somewhere distant, studied from a comfortable distance the way Boötes is. That's the void we're inside of, right now, using as our baseline for every measurement we make about the rest of the cosmos. Researchers don't love sitting with that. There's a strong pull in this field toward null results. The boring answer, the one that confirms the universe looks the way the models say it should, and nobody's address needs a special footnote. A universe where every neighborhood is statistically ordinary is a universe where measurements can be trusted without constant hedging about whether your particular corner of space is secretly warping the numbers. Finding out your own neighborhood might be the exception isn't the kind of discovery that gets celebrated quietly. It's the kind that gets double-checked, reanalyzed, and argued over for years before anyone fully accepts it. That discomfort is worth carrying forward, because Boötes doesn't offer the luxury of averaging the problem away. Our own underdensity is modest enough that you can squint and call it a statistical fluke, an unlucky roll that happened to land where we're standing. Boötes takes that same basic tension, the same quiet violation of an assumption cosmology treats as close to foundational, and forces it into the room at a scale that leaves far less room for comfortable explanations. Pull back far enough from any single galaxy, and a pattern shows up that took cosmologists decades to fully map. Matter doesn't scatter randomly across space. It threads itself into filaments, long strands connecting one dense region to the next, with those filaments meeting at nodes where galaxies cluster thick enough to form the massive structures holding the whole arrangement together. Walls of galaxies stretch between the nodes, and in the gaps between the filaments and the walls, there's room. Emptier stretches, sitting in the spaces the threads don't reach. Cosmologists call the whole arrangement the cosmic web. And once you've seen a map of it, the universe stops looking like a random scatter of light and starts looking like something closer to a structure with architecture. Voids aren't the exception inside that architecture. They're most of it. By volume, the overwhelming majority of the universe falls into these gaps between filaments rather than into the filaments themselves. Galaxies are the part that gets photographed, mapped, and named. Emptiness is the part that actually fills most of the space. But typical voids aren't as clean as their name suggests. Most carry at least a faint filament running through them somewhere, a scattering of galaxies threading through the gap, even if the overall density stays low. The emptiness in an ordinary void is relative, not absolute. There's still something in there, however sparse, connecting it loosely back to the structure surrounding it. Boötes doesn't have that connective tissue. Beyond the tube of 60 galaxies running through its center, the rest of the interior is close to bare, without the faint threading of filaments that softens the emptiness in a typical void. Whatever normally links an underdense region back into the surrounding web simply isn't present here in any meaningful amount. The 5 superclusters ringing its boundary reinforce how different this structure really is. In a standard void, the surrounding cosmic web wraps around loosely, filaments curving past on their way to somewhere else, treating the void as one gap among many along a much longer thread. Around Boötes, those 5 superclusters don't behave like passing neighbors. They sit at the edges like walls enclosing a courtyard, defining the boundary rather than simply bordering it in passing. That distinction matters more than it might first appear. A gap between threads is still part of the weave, still connected to the rest of the structure by whatever thin material happens to pass through it. What surrounds Boötes doesn't read like a gap in the weave at all. It reads like a tear, a place where the connective material that should be threading through simply isn't there, leaving behind bare boundary walls instead of the gradual, low-density transition a normal void would show. A tear demands a different kind of scrutiny than an ordinary gap does. It's not enough to ask why matter is sparse in that direction. Something has to explain why this specific pocket got cut off entirely from the surrounding weave, cleanly enough that even gravity itself starts to look like an insufficient explanation once you run the numbers against every alternative theory of how matter should behave on a scale this large. Something else has started showing up in the velocity data near the void's edge, and it's smaller than the tear in the cosmic web, but arguably stranger. Galaxies sitting right at the boundary of Boötes are moving a little faster than Einstein's equations say they should. Not by a dramatic margin, a few percent, the kind of discrepancy that could plausibly vanish under closer scrutiny, chalked up to measurement noise or an uncertain distance estimate somewhere in the chain. Except it hasn't vanished. Multiple independent observations, run by different teams using different instruments, keep landing on the same small but consistent gap between what general relativity predicts for these galaxies and what they're actually doing out there. The first place anyone looks when velocities run high is hidden mass. Extra gravitational pull needs a source, and the obvious candidate is matter sitting somewhere nearby that hasn't been accounted for, quietly adding its own pull to whatever's already expected. Gravitational lensing surveys were built to catch exactly that kind of hidden mass, reading the way background light bends as it passes near a gravitational source, too faint to see directly otherwise. Point those surveys at the regions surrounding Boötes' edge, and they come back clean. There's no undetected clump of matter lurking nearby large enough to account for the extra speed. Whatever's pushing these galaxies, it isn't hiding mass we simply failed to find. That's where modified gravity enters the conversation. Not as a fringe idea, but as a serious candidate with its own body of supporting theory. The basic proposal is that gravity itself might behave slightly differently once you're operating across the largest scales. The universe offers strong enough at galactic and solar system scales to match everything Einstein predicted, but subtly enhanced once you stretch the distances out far enough. Structure formation under a theory like that wouldn't unfold identically to standard general relativity. It would run a little hotter, a little more efficient at pulling matter together and pushing it apart. Exactly the kind of small excess showing up in the velocities at the void's edge. The trouble is that modified gravity doesn't get to cherry-pick which observations it explains. A theory built to account for these void edge velocities has to also account for everything else general relativity already gets right, and that includes the cosmic microwave background, the ancient light carrying the clearest fingerprint of the early universe's structure. This is exactly where most versions of modified gravity run into trouble. They can match the velocity anomaly at the edge of Boötes reasonably well. They struggle to reproduce the cosmic microwave background with anything close to the precision standard general relativity already achieves. Fix one, and the other slips out of alignment. So the tension sits unresolved, small enough to dismiss on a slow day, persistent enough that nobody serious is dismissing it. A few percent of extra velocity, showing up reliably at the boundary of one of the strangest structures in the observable universe, isn't proof that Einstein got something wrong. But it's not nothing either, and it's exactly the kind of loose thread that's expensive to leave dangling once you notice it. Which is precisely why the newest generation of survey missions isn't treating emptiness as background noise to work around anymore. They're pointing directly at it, on purpose, because a discrepancy this small might only resolve itself once someone builds an instrument capable of measuring voids with enough precision to settle the argument outright. That instrument already has a name and a launch date behind it. The Euclid Space Telescope went up with a mission that sounds almost too broad to be useful. Map the positions of galaxies across roughly a third of the entire sky, building the largest three-dimensional atlas of the universe ever attempted. Billions of galaxies, catalogued and positioned with enough precision to reconstruct the cosmic web at a level of detail no previous survey has managed. Voids sit at the center of that mission, not as background to be skipped past on the way to more interesting targets, but as the actual instruments doing the measuring. That's a shift worth sitting with for a second. For most of the history of galaxy surveys, emptiness was the thing you subtracted out, the negative space around whatever you were actually trying to study. Euclid inverts that. The size of a void, the shape it settles into, and the rate at which it grows over cosmic time all carry information that dense, crowded regions simply can't offer as cleanly, because there's no competing gravitational noise drowning out the signal. Here's why that works. A void's growth rate is sensitive to the balance between whatever gravity remains inside it and the push of dark energy expanding it outward. Track that growth across enough voids, at enough different distances, and you're effectively watching the tug-of-war between those two forces play out at different points in cosmic history. That's a direct constraint on something cosmologists call the dark energy equation of state, a technical way of asking one deceptively simple question. Does dark energy behave like a fixed, unchanging property of space itself, or does its strength shift over time? That distinction matters more than it might sound like it should. If dark energy is a true constant, unchanging, no matter how far back you look, the universe's expansion follows one trajectory, accelerating steadily and predictably into the future. If dark energy instead behaves like a field, something that can strengthen or weaken depending on conditions, the trajectory changes entirely, and so does everything downstream of it. The long-term fate of the universe, whether expansion keeps accelerating forever or eventually shifts into something else entirely, hinges on which of those two descriptions turns out to be correct. Voids are where that question gets answered first, precisely because they're the places where dark energy's influence shows up loudest relative to gravity's competing pull. A confirmed deviation from the constant model, caught in how voids grow rather than in any single dramatic observation, would ripple outward into every corner of cosmology built on the assumption that dark energy holds steady. It wouldn't just adjust one number, it would rewrite the forecast for how everything ends. None of that resolves the specific puzzle sitting inside Boötes, and the Euclid mission isn't built to answer that question directly. What it offers instead is context. a way of finding out whether Boötes is a true outlier among voids or simply the most extreme example scientists have happened to study closely so far. That answer is still years away, buried inside a dataset that's only beginning to take shape. But dark energy doesn't wait for missions to finish before leaving evidence behind. Some of its clearest fingerprints are already sitting inside light that's been crossing the universe for billions of years, encoded in a signal so faint it took decades of careful measurement just to confirm it exists at all. There's a piece of physics called the Sachs-Wolf effect, and it explains what happens when ancient light falls into a void and climbs back out the other side. A photon entering a region of lower gravitational potential picks up a small burst of energy, the same way anything gains speed falling into a dip. Climb back out of that dip, and the photon should lose exactly what it gained. Energy in, energy out. A clean cancellation that leaves no trace behind. That cancellation only holds if the dip stays put while the photon crosses it. In a universe sitting still, gravitational wells don't change shape between the moment something falls in and the moment it climbs back out. But nothing about the Boötes Void is sitting still. It's expanding while that photon makes its crossing, which means the well the photon fell into isn't the same well it's climbing out of. The floor has shifted underneath it, stretched shallower by the time the far edge arrives. That mismatch leaves a surplus behind. The photon exits the void carrying slightly more energy than a static universe would ever allow. A fractional gain too small to notice in any single photon, but large enough to show up once you average across the enormous number of photons that have made this same crossing. Astronomers describe the result as an ultra-faint shift in temperature, a whisper of extra warmth stamped onto the cosmic microwave background wherever that ancient light has passed through a large void on its way here. Measurements have confirmed this signature is real. Stack enough voids together, and the cosmic microwave background shows exactly the kind of subtle warming this mechanism predicts, a pattern too consistent to write off as noise. It's a small number buried in data that took years of careful work to extract, but it holds up. What makes this particular signature valuable isn't just that it confirms a theoretical prediction, it's that this is one of the only pieces of evidence showing dark energy actively doing something to Boötes right now, in the present, rather than something inferred indirectly from how the void formed billions of years ago. Every other clue in this investigation points backward, towards some ancient process that already finished playing out. This one is live. The void is still expanding. That expansion is still stretching the gravitational well a passing photon falls into, and that ongoing stretch is still leaving its mark on light crossing through it at this very moment. Dark energy isn't a historical explanation here. It's an active ingredient, caught in the act. That's a strange kind of reassurance, and a strange kind of warning at the same time. Reassurance because it confirms the basic mechanism holding this entire investigation together actually behaves the way the models say it should. Warning because Boötes isn't the only large void carrying a signature like this, and somewhere else in the sky, a colder, stranger version of the same story, has been sitting in the data since 2004, waiting for someone to figure out exactly how big the thing responsible for it really is. In 2004, researchers combing through the cosmic microwave background found a patch of sky that stood out for the wrong reasons. It sat in the direction of the constellation Eridanus, colder than the surrounding background by a margin too large to shrug off as ordinary statistical noise, and considerably wider than typical fluctuations in the ancient light. Astronomers called it, without much ceremony, the cold spot. The Sachs-Wolf mechanism gave them an obvious place to start looking for a cause. If a void large enough and deep enough sat along that exact line of sight, the same effect explaining Boötes' faint warming should produce the opposite signature at a larger scale. A genuine chill stamped into light that had to cross an enormous stretch of underdensity on its way here. Search that patch of sky for a matching structure, and something turned up. Researchers identified a candidate void in that direction, one that's since picked up its own name, the Eridanus supervoid. The trouble is that the numbers don't quite close. Run the Sachs-Wolf math on the Eridanus supervoid using its measured size and depth, and the cooling it should produce falls short of what the cold spot actually shows. Not by a small margin either. One void, however large, doesn't appear to carry enough emptiness by itself to fully account for the anomaly sitting in that patch of sky. Something else has to be contributing, and nobody's identified exactly what. That gap has left the field split. Some researchers treat the discrepancy as evidence that the cold spot is simply a statistical fluke, an unlucky cold patch that would have shown up somewhere in the sky, eventually just from random variation, with the Boötes Void as a partial but incomplete contributor, rather than the full explanation. Others reach for stranger physics entirely, the kind of exotic mechanisms that tend to surface whenever a clean answer refuses to add up on the first pass. Nothing on that end of the spectrum has gathered enough evidence to settle the argument in either direction. What makes Boötes useful here isn't that it explains the cold spot. It doesn't, and it isn't trying to. What it offers is a benchmark, a well-measured, well-understood supervoid whose Sachs-Wolf signature has already been confirmed and calibrated against real data. Compare that signature against what the Eridanus supervoid should theoretically produce at its own size, and researchers get a working sense of how much cooling a void of a given scale ought to leave behind. Boötes becomes the ruler other supervoids get measured against, the known quantity that makes the unknown ones easier to interrogate. That still leaves the cold spot standing as an open case, a colder and possibly larger cousin to Boötes, sitting unresolved in the same sky that's been quietly generating anomalies for decades. Two mysteries now instead of one, tied together by the same physics, and neither one fully solved, which is precisely the kind of unresolved tension that pushes an investigation like this away from the natural explanations that almost work, and toward the theories nobody's especially eager to defend out loud. Every serious researcher studying Boötes will walk you through the void merger model, the timing problem, the Sachs-Wolf measurements, all of it delivered with the careful confidence of someone standing on solid ground. Ask that same researcher about Dyson spheres, and something shifts. The tone changes. Nobody wants their name attached to this one on the record, and yet the idea keeps surfacing anyway, because it's the one explanation that actually accounts for every strange feature at once. The premise starts small, with an idea that's been sitting in serious astrophysics for decades. A sufficiently advanced civilization, the reasoning goes, wouldn't just live near a star. It would eventually want to capture that star's entire energy output, wrapping it in a structure built to collect radiation that would otherwise just spill uselessly into space. Scale that ambition up from a single star to an entire galaxy, and you get a structure large enough to intercept a galaxy's total light output, converting a blazing point of energy into something that reads from the outside
as nothing at all.
Push that logic further, and the specific numbers behind Boötes start looking almost engineered for this explanation. Something in the neighborhood of 10,000 galaxies missing, exactly the deficit standard density models predict for a volume this size. 60 left visible, clustered along that same cylindrical tube running through the center. Under this framing, the void isn't empty because nothing formed there. It's empty because something already finished consuming almost everything that did. The obvious problem is what a structure like that would have to leave behind. A civilization capturing the energy output of 10,000 galaxies doesn't get to keep that energy invisible. Thermodynamics doesn't allow perfect efficiency, and whatever gets absorbed eventually needs somewhere to go, radiated back out as waste heat, most likely in infrared wavelengths, exactly the kind of signal modern sky surveys are built to catch. Search the region for that signature across every wavelength available, and nothing comes back. No infrared excess. No unexplained heat signature marking the boundary where visible galaxies give way to whatever's supposedly hidden beyond them. The void looks cold and quiet in every band anyone has checked, which is precisely what you'd expect from actual emptiness, and precisely what you wouldn't expect from 10,000 galaxies quietly venting waste heat into the dark. That absence is worth stating plainly rather than dancing around. This is the weakest explanation on the table, by a wide margin, measured against anything resembling observational support. It survives in conversation, not because the evidence points toward it, but because the void itself is strange enough that ruling out every possibility, however unlikely, feels like part of doing the job properly. An idea this speculative earns its place in the investigation only because everything else about Boötes has already refused to behave the way it should. Which raises an uncomfortable question worth sitting with before moving past it entirely. If a hypothesis this far outside mainstream physics still gets mentioned in serious rooms, What does that say about how much the natural explanations have actually managed to close the case? Not much, as it turns out, which is exactly why the next candidate worth examining doesn't come from speculation about advanced civilizations at all. It comes from an idea borrowed from the edge of theoretical physics itself, one that doesn't require intelligence, only the strange mechanics of a universe that might not be the only one there is. Eternal inflation starts from a strange but well-established piece of theoretical physics. Inflation, the explosive expansion that stretched the infant universe in its first fraction of a second, might not have been a one-time event. In some models, inflation never fully stops everywhere at once. It keeps happening in patches, spinning off what theorists call bubble universes, each one a separate pocket where inflation ended locally and a universe like ours began to take shape. Ours would be one bubble among an uncountable number of others, drifting inside a much larger inflating space that never stopped expanding around us. Bubbles that form close enough together in this picture don't necessarily stay isolated from each other. If two of them expand toward one another before the space between them stretches too far to close the gap, they can collide. A collision like that wouldn't destroy either universe. It would leave a mark, a disturbance rippling outward from the point of contact, altering the density of matter in a roughly circular pattern centered on wherever the two bubbles first touched. Run that disturbance forward through billions of years of structure formation, and a collision scar from the earliest fraction of a second could plausibly still be visible today, written into how galaxies and voids are arranged across an enormous stretch of sky. That's the mechanism researchers have gone looking for, searching the cosmic microwave background for exactly this kind of circular signature, a faint ring-shaped pattern that wouldn't match the random scale-invariant fluctuations standard inflation predicts everywhere else. Several searches have reported candidate patterns matching roughly what a bubble collision should look like. None of those results have held up as clean, uncontested detections. The patterns found so far sit close enough to the noise floor that different teams analyzing the same data have reached different conclusions about whether anything real is there at all. It's the kind of result that stays in the literature without ever quite graduating into confirmed physics. And even setting aside whether any collision signature exists in the sky at all, there's a more specific problem for using this idea to explain Boötes directly. Nothing about the void carries a signature that's uniquely tied to a bubble collision rather than to ordinary structure formation. A collision scar and a supervoid formed through standard gravitational processes could, in principle, look similar enough from the outside that distinguishing between them would require evidence nobody currently has. Boötes doesn't come with a fingerprint pointing specifically at a multiverse origin. It comes with an anomaly that a multiverse origin could theoretically explain, which is a much weaker claim than researchers finding actual matching evidence. That gap between explaining something and having a unique piece of proof for it is exactly what keeps this idea sitting on the far edge of the investigation, rather than anywhere near its center. A multiverse collision is untestable with anything resembling current technology, not because the physics is unreasonable, but because there's no experiment on the horizon capable of distinguishing this scenario from the ordinary alternatives sitting right next to it. It's appealing precisely because it's dramatic, and because it borrows credibility from genuinely serious theoretical work on inflation. Unproven is still the honest word for it. Two more ideas remain worth examining before closing out this stretch of the investigation, and both of them come from the same general neighborhood of theoretical physics, dealing not with other universes but with structures that may have formed inside our own before it had finished settling into the shape it holds today. Cosmic strings belong to a category of physics that sounds almost too strange to take seriously, and yet they show up as a genuine prediction in several well-regarded theories about the earliest moments after the Big Bang. As the infant universe cooled, certain symmetries in the underlying physics would have broken, and the theory goes that this breaking could have left behind defects, thin threads of concentrated energy stretched across space, thinner than an atom but carrying enough mass to bend light and pull on matter across enormous distances. If a cosmic string happened to pass through what became Boötes, the gravitational disturbance it left behind could theoretically have discouraged matter from gathering there at all, leaving a void where a string once cut through. That idea runs into a wall the moment you check it against what's actually been measured. Decades of searches, using gravitational lensing surveys and detailed scans of the cosmic microwave background, have pushed the allowed strength of any cosmic string network down to levels far too weak to carve out something the size of Boötes. Strings might exist. Current limits don't rule them out entirely. But whatever's left of the allowed parameter space describes something too faint, too rare, to explain a void this large and this complete. The math simply doesn't stretch that far. Domain walls carry a similar shape of idea, built from a different piece of the same broken symmetry physics. Where a cosmic string is a one-dimensional thread, a domain wall is a two-dimensional boundary, a surface separating regions of space that settled into different versions of the same underlying vacuum state after the early universe cooled unevenly. A wall like that would carry its own gravitational signature, distinct from a string's, and in principle could account for an unusually sharp boundary around an underdense region. The same observational limits that constrain cosmic strings apply here too, and they land in the same place. Nothing in the data supports a wall large or dense enough to be responsible for what's sitting in Boötes. False vacuum decay pushes the same family of ideas even further out. The premise is that the vacuum of space itself might not be sitting in its lowest possible energy state, and that somewhere, at some point, a patch of that vacuum could tunnel into a truer, lower energy configuration, releasing an enormous burst of energy as it does. A decay event like that wouldn't leave a quiet, well-behaved void. It would leave scars, distinct and dramatic, sudden shifts in the fundamental behavior of physics at the boundary, along with an energy signature loud enough that no survey looking in that direction could plausibly have missed it. Nothing like that shows up anywhere near Boötes. Set all of it side by side, and the pattern is consistent. Cosmic strings, domain walls, false vacuum decay, theoretically real, technically permitted by the equations, and constrained hard enough by observation that none of them can be pinned to what's actually sitting in the sky. They're the ideas physics allows without evidence ever asking them to show up. Put every explanation gathered so far on the table at once, and the contrast between the two piles is stark. On one side sits standard cosmology, void merger theory, quantum fluctuations amplified by gravity, dark energy accelerating expansion once matter thinned out enough to let it dominate. Strained in places, yes. The timeline runs uncomfortably tight. The symmetry sits stranger than the models are built to expect, but nothing about it requires physics that hasn't already been confirmed somewhere else. Every mechanism doing the work here is a mechanism astronomers already trust, already use, already measure daily in 100 other contexts. The other pile looks nothing like that. Dyson spheres need an advanced civilization nobody has found a trace of. Multiverse collisions need other universes nobody can observe. Cosmic strings, domain walls, false vacuum decay all need physics that remains theoretical, permitted by the equations, but never once confirmed by an actual measurement. Not one exotic explanation on this list gets by on established science alone. Every single one needs something new bolted on. A new particle, a new force, a new civilization, a new universe. That's the dividing line, and it's not a subtle one. Occam's razor exists for exactly this situation, and it doesn't split the difference here. Given two explanations that both account for an observation, the one requiring fewer new assumptions wins by default, not because it's guaranteed to be correct, but because it's the one that doesn't ask you to invent something extra just to make the story work. Weigh the standard cosmological explanation for Boötes against any version of the exotic pile, and the razor cuts hard in one direction. A strained but internally consistent application of known physics beats a clean explanation that only works if you're also willing to accept the existence of something science has never once detected. None of that amounts to a clean win, though, and pretending otherwise would be dishonest about where this investigation actually stands. The natural explanation remains the leading one. It also doesn't fully close the case. The timing problem hasn't resolved itself, just because the alternative explanations look worse by comparison. The perfect symmetry hasn't found a mechanism that produces it reliably. Sorting the theories by plausibility tells you which explanation to trust more. It doesn't tell you that the trusted explanation has actually finished answering the question. That's the uncomfortable place this leaves things. Ruling out the exotic doesn't manufacture proof for the mundane. It just narrows the field down to the version of events that asks the least of you. while leaving the actual mechanism still only partially accounted for. Which means the deeper tension driving this entire investigation hasn't gone anywhere. It's still sitting exactly where it was before any of these theories got weighed against each other, and it's about to resurface in a form that's even harder to wave away than the timing problem already was. The tension resurfacing here is the timeline problem, except this version of it doesn't come from simulations running gravity forward and falling short. It comes from something much older and much harder to argue with: the stars themselves. Globular clusters, those tightly packed collections of ancient stars orbiting on the outskirts of galaxies, function as independent clocks. Astronomers can measure the ages of the oldest stars inside them by tracking how far those stars have progressed through their nuclear fuel, a process that runs on a fixed and well-understood schedule. White dwarfs offer a second, unrelated clock, cooling at a steady, predictable rate once a star has burned through everything it has and collapsed down into a dense, quiet ember. Neither method depends on assumptions about cosmic expansion. Neither one cares what void formation theory says. They're reading age directly off the physics of individual stars, and both keep coming back with numbers that place the oldest visible stars close to the universe's own age, with almost no room to spare. That's where the local expansion rate discrepancy, the same one raised earlier in the investigation, stops being an abstract measurement problem and turns into something closer to a paradox. If the faster local expansion rate turns out to be the true value rather than some artifact of measuring from inside an underdense neighborhood, the universe's calculated age shrinks along with it. Run the math using that higher rate, and the universe comes out younger than the stars sitting inside globular clusters, stars whose ages were measured through a completely separate method that has nothing to do with expansion rates at all. A universe can't be younger than the oldest things living inside it. That's not a subtle inconsistency, easily smoothed over with a slightly different assumption somewhere in the model. It's a direct contradiction. One method saying the clock started at one point, another method insisting something inside that universe had already been burning for longer than the clock allows. No single adjustment resolves it cleanly. Nudge the expansion rate to fix the age problem, and the local measurements stop matching what's actually observed nearby. Nudge the stellar ages instead, and you're rewriting nuclear physics that's been checked and rechecked against far more evidence than the expansion rate has. This connects directly back to the Hubble tension raised earlier in the investigation, the same stubborn 9% gap between the early universe measurement and the local one. That gap isn't just a disagreement between two numbers anymore. Once stellar ages enter the picture, it's a disagreement with a body attached to it. Physical evidence in the form of ancient stars that existed and burned, regardless of which expansion rate turns out to be correct. Every thread pulled on so far in this investigation, the timing problem inside Boötes, the perfect symmetry nobody can explain, the local underdensity biasing our own measurements, keeps leading back to the same unfinished business. Something in the standard model is either incomplete or misapplied somewhere along the chain, and nobody has yet identified exactly where. Go back to the 60 one more time, because they're the closest thing this investigation has to hard physical testimony. Not a simulation output, not a statistical model run backward from an assumed density. Actual galaxies, sitting exactly where instruments can point at them, carrying whatever evidence survived the process that hollowed out everything around them. If Boötes has a witness stand, this is it. Treat them as a controlled experiment rather than a curiosity, and the value of that tube sharpens considerably. Nowhere else in the observable universe do you get 60 galaxies removed this thoroughly from the gravitational noise of neighbors, from the mergers and tidal disturbances that shape how galaxies evolve almost everywhere else they've ever been studied. Every variable that normally complicates the picture of galaxy evolution has been stripped away here by circumstance. What's left ought to be the clearest possible read on how a galaxy behaves when nothing else is pushing on it. And the read keeps coming back stubborn. Sustained star formation with no obvious source of fresh gas. Spiral structure holding its shape without a nearby galaxy to keep the pattern refreshed. These aren't small footnotes sitting at the margins of the data. They're the two features that should have failed first, and they're the two features holding up best. Which opens a possibility worth taking seriously, rather than filing away as background noise. Maybe isolation itself does something to a galaxy that current models haven't fully accounted for. Not damage, not decay, but a different track entirely. One where the absence of disruption isn't a void in a galaxy's development so much as a distinct set of conditions with its own internal logic. Standard galaxy evolution theory was built almost entirely from observations of galaxies embedded in company, shaped by proximity, as the default assumption running underneath the whole framework. 60 galaxies that never got that company are the one dataset capable of testing whether that assumption was ever actually necessary, or whether it was just the only condition anyone had available to study until now. That reframes what the 60 are actually doing inside this investigation. They aren't simply survivors marking where the void failed to finish the job. They're a second mystery riding inside the first one. Evidence that the emptiness surrounding them isn't the only part of Boötes that current models can't fully explain. The void's size and shape sit there, refusing to add up on one side of the ledger. The galaxies sitting inside it, refusing to look as isolated as their circumstances should demand, sit there, refusing to add up on the other. Which means the case was never only about the missing 99%. It's just as much about the fraction that didn't vanish, and the fact that nothing about them looks damaged by the conditions that should have left a mark. That's a strange thing to call unfinished business, a handful of ordinary-looking galaxies floating in the dark. But that's exactly the shape the unresolved question takes once you zoom out far enough to see where it's actually pointing towards something larger than one void, something that touches how matter organizes itself everywhere the universe has room to be empty. Something touching how matter organizes itself everywhere the universe has room to be empty. That's not a poetic flourish. It's a direct consequence of how dark energy operates, and once you follow the logic forward instead of backward, Boötes stops looking like an anomaly and starts looking like a preview. Dark energy doesn't push evenly against everything. It accelerates expansion hardest, exactly where matter is thinnest, because matter's gravity is the only thing pushing back against that acceleration, and thin regions have the least of it to offer. Inside a void, there's almost nothing left to resist the stretch, which means voids don't just sit passively while the universe expands around them. They lead. They're the regions where dark energy's grip tightens first and fastest, precisely because they've already lost the gravitational ballast that would otherwise slow it down. Run that forward past the boundary of Boötes itself, out to the 5 superclusters ringing it, and the same pressure doesn't stop at the edge just because it's currently pressing against something denser. Those superclusters are massive, but mass isn't infinite immunity from an accelerating universe. Given enough time, the same stretching force thinning out the void's interior starts working on the walls, holding it in, pulling at their outer galaxies, loosening the gravitational bonds holding the whole structure together from the outside in. Walls don't hold forever against a force that never stops accelerating. Zoom out from Boötes, specifically to the cosmic web as a whole, and the pattern repeats at every scale. Filaments connecting one supercluster to another aren't permanent fixtures. They're temporary alignments, held together only as long as gravity's pull across that distance outmatches dark energy's push. As voids everywhere continue widening, those connecting filaments thin out, stretch, and eventually snap one by one, breaking the web apart from the inside rather than any single dramatic event tearing it all at once. Which means the universe you're looking at right now, dense with galaxies, threaded with filaments, wall after wall of matter organized into the cosmic architecture described earlier in this investigation, isn't the default setting. It's a phase, a crowded, structured, comparatively brief window sitting between a smoother early universe and a much emptier future one. And we happen to exist inside the window rather than on either side of it. Push the timeline out far enough, and the picture inverts entirely. Structures like Boötes, currently treated as the exception, the anomaly demanding explanation, become the ordinary condition instead. Isolated galaxies drifting through enormous empty distances stop being a puzzle confined to one unlucky patch of sky and start being what nearly everything eventually looks like. Once enough time has passed for dark energy to finish the work it's already doing to the walls around Boötes right now. That reframes the entire investigation in a way none of the earlier sections quite managed to. The real mystery was never why this one void exists when the rest of the universe still looks crowded. The real mystery is why we still live in a universe crowded enough to ask that question at all, when everything currently known about how this process ends points toward emptiness being the rule, and rooms like ours being the exception that won't last. Here's what's actually known. Stated plainly, one final time. A sphere of near total emptiness sits 700 million light-years away, 330 million light-years across, holding 60 galaxies where standard density would demand somewhere close to 10,000. That's the shape of the case file, and every chapter of this investigation has done nothing more than circle those same three numbers from a different angle. None of it closes clean. The timeline still doesn't fit comfortably inside 13. 8 billion years, no matter how generously the merger models get stretched. The symmetry still reads as too precise for a process that should leave lumps and seams behind. And the 60 galaxies still sit there looking healthier than isolation. This extreme has any right to allow spiral arms intact, star formation running, refusing every prediction that said loneliness should leave a mark. Three open threads, none of them resolved, all of them still sitting exactly where earlier chapters left them. That's not a failure of the investigation. It's an honest account of where the evidence actually stands. Euclid is still building its atlas of voids across a third of the sky, still years from a dataset large enough to tell us whether Boötes is a true outlier or simply the largest example scientists have studied closely so far. The same surveys hunting for cosmic string signatures and Sachs-Wolf imprints around other supervoids are still running, still adding data points, still narrowing the range of what's possible without yet delivering the number that settles anything for certain. There's a temptation, standing at the end of something like this, to manufacture a bow to tie around it, to pick the least strange explanation on the table and declare the case solved because it's the one that asks the least of you. That would be dishonest about what's actually been shown here. The natural explanation remains the strongest one. It also hasn't finished its work. Pretending otherwise wouldn't honor the investigation. It would just end it early. So the tension stays intact, exactly as it should. You now know the numbers nobody can fully explain, the timeline that refuses to close, the galaxies that won't behave the way their circumstances demand. That's not a burden. It's the honest shape of an open case, carried forward rather than filed away. Somewhere else in this same universe, another anomaly is sitting in the data, waiting for someone to notice. It doesn't add up either. When it surfaces, this investigation continues.